Hey guys, let's talk a little bit about potential and current. So we're gonna connect potential difference to current. We're gonna see how exactly are these related. So first, let's just talk about a battery. So we have some battery. Just draw, and then we connect the ends, the terminals of it, with some wire. Okay, so inside of this battery, inside of it, from one end to the other, we have a potential difference of the battery. We'll say VB. And so this potential difference across the battery, if I were to measure it, if we were to actually be able to measure and say right at this terminal, what we would see is that the actual potential at this point would be 0. And then if I came over to this one, then the potential, say this was let's say it's a 9-volt battery, then this would be 9 at the positive terminal. So what you can see is that the battery, the potential difference between them is also the potential difference across the wire. And that's the whole essence. So it creates this like downhill flow of positive charge. Remember, we're talking about the conventional flow. So it's the positive charges flowing around it. It's going to go from high potential to low potential. And so basically what we're going to get is that the potential difference of the battery is equal to the potential difference of the wire. So if I were to measure it outside of the battery, just across the wire, I would get the same potential difference that exists in the battery. And this is key. So a battery supplies potential difference. The battery supplies potential difference. Now, if I were to open this up, and so maybe an analogy would be over here at the positive terminal. So we'll say at the positive terminal, we have high potential. And so the current then wants to flow down into the negative side. These are positive charges, remember. So positive charges would flow downhill, and that's what's happening in the circuit. So the potential difference that the battery supplies, that determines the direction of the current. And you saw this in a video of how we can recharge the batteries. What we do is we actually flip the direction of the current. So you push it back, and that's pushing all the electrons in the other direction. Okay, so the potential difference explains the direction of current, but what about the magnitude? So how about the magnitude of the current? In other words, how strong is it? The magnitude of the current. Well, there's a couple things that affect this. One, what we can do to test it, you could say, okay, well, let's take a 9-volt battery and let's stack it on and put another one on top of it. And so what this is called in series. So now I have two 9-volt batteries. So the potential difference across this one is 9 volts. The potential difference across this one is 9 volts. And then if I connected it with a wire, I would short it out and start a fire and probably blow up the batteries, but we're just talking in ink. And so if I measured, now we want to know what's the potential difference across the wire. That would be 18 volts. And since I have a higher potential difference, I'll have higher current. So it seems that the current is going to be proportional to the potential difference of the battery. And that makes sense. If I put a whole bunch of batteries, I'm going to get a lot more current flying through it. But what about the wire itself? So what if I were to take it and I changed it? And now instead, what I did is I made this wire come all the way out here, and I doubled, or about doubled the length of it. So now I have a much longer wire. What do you think is going to happen to the current? Well, it just gets harder to, there's a lot more distance that has to be covered, and so the current would actually decrease as the length of it increases. The current will decrease. So what we can see is that it's going to be proportional to the inverse of the length of the wire. Yeah, I'm sorry. I got sidetracked there. Because I don't know if I want to go down this route. You know what? Let's not talk about the length yet. Yeah, it doesn't matter. Okay, so we could take it long, but what if I made it really, really fat? What if I made it into a really, really fat wire? Then what's going to happen? Well, it gets easier to push them through. And so what we see is that there's some quantity of the wire that's determining it. It's determined by the length, it's determined by the cross-sectional area, it's determined by the material itself. And altogether, that's just called the resistance. So instead of doing length, let's just change this. It's inversely proportional to the resistance of the wire. And so what we get is our next equation, that the current is equal to the potential difference over the resistance of the wire. So the resistance is determined, we'll talk about that in just a second. As I increase the resistance, I get less current. If I increase the potential difference source, I will get more current. It just kind of makes sense mathematically. All right, what about this resistance though? What does that resistance depend on? And so I started to get into it. Sorry about that, got distracted. So resistance. I think I misspelled that. I think it's an E. Anyway, so you have some, let's just say we have some wire here. And we have some charges flowing through it. Then what we can do is we can either, it will think if I made this like twice as long, it's going to take more energy to push these through. So it's going to resist the motion more. There's just more particles that have to be pushed through in order to get all the way through the length of it. So the resistance is going to be proportional to the length. But if I took the same wire and I just increased the diameter of it, or the cross-sectional area, well, now there's a lot more that can flow through, and it's a lot easier to push things through. So the resistance is proportional to the inverse of the area. And then if you think about it, if I made this wire out of wood, how about wood versus copper? Why do we use copper wire? Well, because it has something called low resistivity. And so it's also proportional to the resistivity, which we say rho. We use rho. It's like this little p. So that's rho. And that is the resistivity of the material itself. So this is determined by the material. It also depends upon the temperature. Temperature is not going to show up in our equations, but it's important to know that as the temperature goes down, the resistivity goes down. And so if I want something that is a really, really, really good conductor, I can make it really, really, really cold. And this gets into things like superconductors. We make them very, very cold, and we can move electricity through it very easily, very, very low resistance. So resistivity, these are just quantities they'll be given to you. The higher the number, the more the resistance, and then the cross-sectional area and the length of the wire. These are the things that determine the resistance. So let's put it all together. Scroll down a little bit. So what we end up with is that the resistivity equals the resistance equals the resistivity times the length of the wire divided by the cross-sectional area. That's how we would determine the resistance. And then we could use that to determine the current if I know the potential difference. Let's see, was there anything else that I wanted to talk about here? Well, we could look at units, maybe. So the units on resistance are going to be the ohm. So it's a little sigma. My sigma is not very good. And this is an ohm. 1 ohm equals 1 volt per amp. And that comes from this one. If I rearrange it, it would be R is delta V over I. So it's a volt per amp. That's an ohm. Yeah, and I think that's it. The only other thing would be, kind of a cool way that we use this is to measure body fat. So in my bathroom, I have a bathroom scale. And when you get on it, there's these two little metal plates where you put your feet. So you stand there like so. And so the scale gives you your mass, but it also measures your body fat percentage. Because inside of your body, you have different kinds of tissue, but fat has a high resistivity. And so it just measures the resistance of a small electrical current through your body. And based on that, it can calculate the resistance of the fluid, so it can determine the amount of fat that's in your body. So this is an easy way that we can apply it. We can also, you can test water purity. That's another way. So if you had a pipe of water, H2O moving this way, what you can do is connect an electrode to one side and an electrode to the other side. Connect these to a potential difference, and then the electrical current will flow through the water. And then what you can do is you can then measure the resistivity of the water, and you can see what other kind of elements are inside of it, how pure the water is, because we know the resistivity of pure water. So is it up or down? You can test for water purity that way. They also do some imaging by passing a small current like through your chest, kind of like X-ray. The certain materials give more resistance, so it creates a different image on the other side. Anyway, there's all sorts of applications of this. You need to know this, it's on your equation sheet, and this. So this section is just going to be a lot of just applying these equations. That's it.